Here in this quiz, we're looking at acid-base chemistry, and for the first question, we're being asked to calculate the pH of a certain concentration of hydrobromic acid solution. Now, the fact that it's hydrobromic acid is key to this problem and is the first step because we need to recognize that this is a strong acid, which means it reacts completely. Remember, strong acids dissociate completely in water, complete reaction of losing that proton, which identifies acidic activity, and the reaction in water can be shown as follows, right? We have HBr in the presence of water makes our H3O plus and our bromide ion. Equivalently, we could write it just as a dissociation, and so this is really the same because H3O plus is just showing that that free proton is carried on water, which is the solvent in all of these. So we can show it like this, but for consistency with the rest of the quiz, I'm going to follow H3O plus notation as our unit for pH and whatnot. With this in mind, right, we have our reaction, and what we're really after when it comes to pH is the hydronium concentration, the H3O plus. And so we say that if we know that it's 0.0230 molar HBr, we can convert this to the amount of hydronium. They're equimolar because it reacts completely, and so it's 0.0230 molar H3O plus. Still good to put this out explicitly. pH is a negative log of this concentration, which we get as 1.64. The second part is asking us to calculate the pH of a solution made by dissolving barium hydroxide in a certain amount of solution. And we're also given that it dissociates completely. So this is akin to the strong acid problem just for a base. We want to follow the same procedure, right? What is the reaction that occurs? And this is complete dissociation. So barium hydroxide goes to barium 2 plus and 2 hydroxides, complete dissociation. This is to say that each mole of solid makes 2 moles of hydroxide. And also very importantly is it can be tempting to say, well, because this is an aqueous solution, I got to plunk water in as one of our reactants. But that's actually not true here, and it's actually not really true for the strong acid case either, even though we can show the water carrying the hydrogen. Water facilitates this reaction. Water separates something when it dissociates completely, but it's not consumed, it doesn't change form, it doesn't even really carry any ions in the same way, for the most part. It facilitates the reaction, but it should not at all appear as a reactant or product when what it's doing is facilitating that dissociation. From this, we can calculate the amount of hydroxide that's formed. This is just stoichiometry, and we have the following here to get us 0.0225 moles of hydroxide. This is the quantity that's going to lead us to the pH because we can get the concentration of the hydroxide. Then we can get the pOH, which is like pH but calculated for hydroxide. And the pH we actually just get right from that, right? pH is 14 minus pOH, and we have a value of 12.75. For the third part, now we're going to transition into looking at weak acids. So hydrofluoric acid, HF, is a weak acid. We have a Ka, and we compare it to nitrous acid, which has its own Ka. And we're going to say, well, if we make equimolar solutions, so both 0.10 molar, which one has the greatest pH? And we want to show our reasoning here, including chemical reactions. And the reactions in the acid-base chapter are always really, really important to put down, and is where I would start. So here are the two reactions. We have HF, hydrofluoric acid, and with water, it does an equilibrium reaction to form the hydronium and the F minus. So very similar to the HBr reaction, except now we have equilibrium, partial dissociation. That HF mostly stays associated with only a fraction turning into F minus and H3O plus. And the same goes for our HNO2. We have partial dissociation. The extent to which these dissociate are determined by Ka. And because we have our Ka values and we see that hydrofluoric acid has a higher Ka, that means it's more product favored. And that means it's going to have more H3O plus at equilibrium. With that, we can determine the pH. And this last part can be a bit of a gotcha question because more H3O plus actually means a lower pH. So the more dissociation we have, the closer that pH is to like 1 or 0, right? That's the most acidic. So it's actually the one that has a smaller amount of H3O dissociated that gives us the greater pH here as the question is asked, and that would be HNO2. The last question is asking about the conjugate base of hydrofluoric acid. We want to state that conjugate base, write the chemical reaction, and then calculate this other related constant, which is Kb. And so here is our conjugate base, right? It's just HF less a proton, and that would be F minus. This is the corresponding conjugate base. And in the presence of water, we have F minus with H2O, so this is a 2 reacting with water. It's going to take a proton from the H2O and leave us with hydroxide, OH minus, and it will recover the hydrofluoric acid. This is why they're conjugates, right? Because when HF loses its proton as an acid, it forms F minus. When F minus gains a proton, it forms HF. And what we want to find out here is Kb. So this is the reaction of F minus, the fluoride ion, that's going to be acting as a base. It's a weak base, and we want to know how weak or not weak would this base be. And as we talked about with acids, that's determined by an equilibrium constant, Kb in this case. So remember that for a weak acid and its conjugate, Ka of the weak acid and Kb of its conjugate will multiply to form the autoionization of water. And so here it's pretty much just Ka times Kb equals Kw. We can get a little bit more strict here. Note that this is at 25 degrees C, for which Kw is equal to 10 to the negative 14, so that's there. And note that it's not the Ka and Kb of the same species. It's the Ka of a weak acid and the Kb of its conjugate. This reaction that's shown here in part 4 is Kb of F minus, and we already have the Ka of HF. So this is what's going to get us 10 to the negative 14. Because of this, we can calculate the Kb of F minus, and it is as follows. This is the equilibrium constant that goes with this weak base reaction for our fluoride ion F minus.